In the last class, we had done this problem, and what we had done was look at this motion and derive the velocities in the Lagrangian and the Eulerian. Derive the Lagrangian and Eulerian velocities of this motion. And then I had a small animation that I wanted to show you but couldn't. So I have fixed the animation. So it will, it's working right now. Okay, I will explain what I exactly want you to take away from this. So we had these velocities, which are the Lagrangian velocities, and these are the Eulerian velocities. As you can see, the Lagrangian velocities are functions of capital X, and the Eulerian velocities are functions of small x. So these are dependent on the current coordinates, and these are dependent on the initial coordinates of a point. So let us first plot the Eulerian velocities. So I have taken this motion and I have drawn a rectangle. I have taken a rectangular region over which I am going to plot this motion as time passes. So this rectangular region is my initial configuration. Then I have taken points on this. I have taken points on this, discrete points on this rectangular domain, and I have allowed time to pass. As time passes, I am going to plot this x1, x2, small x1, small x2 of each of these points, and they are going to therefore displace over this two-dimensional space. Now, that's what you are going to see. Now, at every time, I am attaching an arrow to each of these points, or the displaced position of each of these points. The arrow indicates the components v1 and v2, the velocity of that point at that point of time at its current location. So in this animation, these blue arrows that you see are over a 1x1 region. So I have taken this initial region to be a 1x1 region. Over this 1x1 region, I've taken several points, and these are the velocities of those points as time passes. These are the current Eulerian velocities of each point at their current location. Okay, so so that's the blue ones are the Eulerian velocities. Now I have the Lagrangian velocities also. To get the Lagrangian velocities, I have to give points in coordinates. So through the Lagrangian velocities, what I'm trying to ask is, at some time t, what is the velocity of a particle that was, say, at x1 equal to 0.1 and x2 equal to 0.1 at the beginning in the initial configuration. So this is the point that I'm taking. And then as time passes, I am following the position of this point, following the location of this point, and plotting the capital V1 and capital V2 for that point. So this is that point. This red dot is the point which is moving as time passes. And then what you see, the arrow attached to it that you see is the Lagrangian velocity of that particular point. Now, just in order to understand this 2 points of view, the Lagrangian and Eulerian points of view, just see something, just notice something. Whenever the bottom of the arrow, bottom of the traveling arrow, whenever it coincides with a pre-existing point, whenever it coincides with a pre-existing point, the sizes of the arrow are the same. That means the velocities, whenever the red dot coincides with the tail of an arrow, tail of an pre-existing arrow, that means whenever the current value of 0.1, that point that was initially at 0.1, whenever you plug it in here and you get a x1, x2 at which you already have a v1, v2 plotted, whenever that happens, this capital V1 and small v1, capital V2 and small v2 are the same for that point. So it's basically the same velocity that you're talking about. It's the same velocity that you're talking about. In one case, you are asking what is the velocity of this red point, which was initially at 0.1. In the other case, you are asking, let's say at 1, what is currently the velocity? At deformed location 1, what is currently the velocity? So these are the two different points of view, and I thought that this video that I made explains it somewhat better than my words could. Okay, so that's about Lagrangian and Eulerian. So let's come to what we want to do today. So we have looked at a motion. Okay, so a motion is a mapping. So we are looking at deformation as a mapping. This is an undeformed configuration. This is a deformed configuration. And we have looked at how a point in the current or deformed configuration maps from a point in the corresponding point, one and only one point in the undeformed configuration. In other words, we have looked at motion as a function of capital X and T. So this was my motion. This is how points map from the undeformed to the deformed configuration. Now, the next what we are going to look at is, okay, this point maps according to this function, this vector function. I want to know how the neighborhood of this point maps. So again, I will assume that neighborhood of the point capital P goes to the neighborhood of the point small p. So that is what I'm going to look at. In order to look at that, I will have to introduce, go back to the slide. Yeah. So to look at that, what I want to know is, suppose a small vector d capital X is attached to the point P, and this vector is tangent to some curve that is passing through capital P in the undeformed configuration. And this d capital X, due to the deformation, maps to d small x at small p. So now I want to know what is the mapping between d capital X and d small x. I already know that small x maps as a function of capital X and T, and I want to know how does a small vector emanating from capital P map due to the motion. So this map, the map that takes d capital X and gives you d small x, is denoted by F, or we will denote it by F, and it's called the deformation gradient tensor. As you can see, it's a tensor because it acts on a vector and gives you a vector. That's a second order tensor. So it's called the deformation gradient tensor. Okay, and in initial notation, Fij is, as you may already work out from this vector equation, Fij is given by del xi del x capital J, and xi is a function chi I of capital X and T, so you can also write it as del chi I by del capital Xj, but most of the time we will do it like this. Okay. Also, we have learned that this chi is invertible. So that means that given a d small x, you can get a d capital X back, and therefore f can be inverted. So the inverse of x is the gradient of the inverse map, which we had denoted by chi inverse in the previous class. So chi inverse, remember, is a function of small x and t. Therefore, f inverse is just the motion in reverse. You reverse the motion. So it's like chi inverse in small x. So for chi inverse, this acts like the reference configuration. This acts like the deformed configuration. So f inverse is del chi inverse del small x, which again in initial notation is Fij equal to where chi I is a function of small x and t. So because the motion is one-to-one and the motion is therefore invertible, and if f exists, f inverse also has to exist. Now, you will also realize that this is a gradient. Small x is a function of capital X and t, and I'm taking the gradient of small x with respect to capital X. So this is a special kind of gradient, and in vector notation, we are going to denote this gradient, like I said in the last class, by this symbol. Zero in the subscript indicates that you are taking a gradient with respect to capital X. When we take a gradient with respect to small x, we'll denote it by this. Okay, so please brush up your tensors and make sure that you understand that f is the gradient of the current position with respect to the initial position. What does it tell me? It tells me that how does a small line segment emanating from P, where does a small line segment emanating from P go to in the current configuration? So this map tells me how d capital X goes to d small x. So this talks about the deformation of lines, whereas this talks about the motion of points. Okay, so so this is the deformation gradient tensor, and there are some things about the deformation gradient tensor that we should know. Deformation gradient tensor is a two-point tensor. That has a special meaning, and the meaning will become a bit clearer when we do a couple of problems. But a two-point tensor basically means that it connects a vector in the reference configuration to a vector in the deformed configuration. We will encounter tensors which will take a vector in the take some quantity in the reference configuration to give you a quantity in the reference configuration itself. Similarly, we will deal with vectors that will vectors and tensors that will take inputs in the reference in the current configuration and give you a vector or a tensor in a current configuration. So those are not two-point tensors. Those are not like f. F is something that connects a vector in the reference configuration to give you a vector in the current configuration. So it's a two-point tensor. These are some consequences which we will see later. It is also non-singular and invertible. So f has to be non-singular. There are situations when we have what is known as a homogeneous deformation. In a homogeneous deformation, f is not a function of capital X. F is just a function of t. So we will call such deformations homogeneous deformations, where no matter which point you choose in the reference configuration, at a particular time, you get one f for the whole system. Okay, so f does not vary with position, it just varies with time. So those are the situations which we call, those are the kind of deformations which we call homogeneous. Also, this body might suffer a rigid body rotation and a translation, rigid body translation. So there may be no deformation at all. In that case, F will not be equal to 0, but F will take this special form. The motion in that case is given by Q capital X plus C, where C is the translation of this reference configuration. So reference configuration translates by C, and then it rotates by a rotation tensor Q. Okay. In that case, all points capital X rotate to small x, where small x is given by Q times capital X. Right. So this is the rotated form, but small x has also been translated by C, and therefore small x would be rotation of capital X with Q plus a translation C. So this is the case when the motion is a rigid body motion, and Q is a special kind of matrix which is called a proper orthogonal matrix, proper orthogonal tensor, so that Q transpose is equal to I, which means that Q transpose is the inverse of Q. So Q inverse is equal to Q transpose. So this is the special property of a proper orthogonal tensor, and all rotation tensors are proper orthogonal tensors, and they have this property. So these are special forms of F. This is for F which is independent of position in the reference configuration, and F is equal to Q. So if this is the motion, then del xi del capital Xj is simply Qij, and that's what you get from here. Therefore, F is equal to Q in this case. That is for a rigid body motion, and for a homogeneous deformation, this is your form of F. So let me just stop here for a moment and see if you are getting everything that I'm saying.
Sir, for rigid body motion, F will not consider translation. It will only consider only rotation.
Now, we will try to express the deformation gradient, which is a very important tensor for us, in terms of the displacement. So we have already defined it as Fij equal to del small xi, which is a function of capital X and T, and del capital Xj. We have defined it like this. Now, we have also defined displacements. So we have defined displacements as u equal to small x minus capital X. So for a point, this is the current position of the point at time t, and this is the initial position of the point. The difference between the two vectors is equal to the displacement. Now, we have looked at it in two ways. We have looked at it in the Eulerian sense when we called it capital U, which is a function of capital X and T, where we write this small x as a function of capital X and T minus capital X. So this is one one way of looking at the displacement. We can also look at the displacement as small u equal to small x minus capital X, which is a function of small x and t connected to the inverse of the motion, right? We have also looked at it. So these two are the same quantities, but here small u is a function of the current positions of the point, and here capital U is the function of the initial position of the point. Now, if we now take this definition and write it in terms of tensor initial notation, we'll write ui equal to capital xi, which is a function of capital X, sorry. I don't know, something strange is going on. So let me scratch it off. I'm not being able to erase it some reason. So ui, which is a function of capital X and t, I'm taking this definition, is equal to small x I, which is a function again of capital X and t, minus capital X I. So this is what I'll write it in initial notation. And if I now want to take this, I will do del capital Xj of ui, which will give me del xj of small xi minus delta ij. So when I take derivative of capital Xi with respect to capital Xj, I get delta ij. So this I can now convert to vector notation. So you should be able to look at the initial notation expression and convert it into a vector expression quickly. So this is gradient of the displacement with respect to the initial coordinates. So I put this 0 here. This you should recognize is the deformation gradient itself, and this is the identity tensor. So this is the expression, which means F is equal to the displacement gradient plus I. So this is an important relation that we will use later. So this is F expressed. Here is F expressed in terms of the motion. Here is F expressed in terms of the displacements. So gradient of the motion, this is gradient of the displacement. So you have to add this identity. Similarly, you can start with the Eulerian or spatial description of small u, and I leave it to you to show that gradient then Fij inverse is given by this relation, or equivalently this relation. So Fij inverse is related to the spatial gradient of u, the inverse inverse of the deformation gradient is related to the spatial gradient, where the deformation gradient itself is related to the material gradient. So note the difference in the symbols, nabla symbols here. Just try to prove this yourself. Okay, now that we have learned about the deformation gradient, we can actually establish the connections between spatial and material gradients. So remember, material gradients are gradients with respect to capital X. So let's say for a scalar, it is for a scalar phi, this is your material gradient. These are the components of your material gradient. As vectors, you can write them del 0 phi, you can write as del phi, del capital Xi. Yeah, this is how you write the material gradient of a scalar. Now, if you want to convert this, if you want to find now del phi del small xi, if you want to do this, then you have to realize that phi is a function of, phi is implicitly a function of small x through capital X. So, so phi is a function of, capital X and time, but capital X implicitly is a function of small x. So I can take del phi del xi. To do that, I will do del phi del x capital Xk and del capital Xk del small xi, which is the same as the chain rule of differentiation. So what I'm doing is del phi del capital X1 del capital X1 del xi plus del phi del capital X2 del capital X2 del xi plus del phi del capital X3 . So this is what I am doing. Because of this repeated index k here, you have this implicit summation. We never write it like this, but this k tells us that there's an implicit summation here. So this is del phi del xi, and you would realize that del capital Xk del small xi is actually your inverse deformation gradient, and this can be written as del phi del x k f inverse ki. This is how you can convert. If you know del phi del xk's, if you know the derivatives of phi with respect to capital X, you can use the deformation gradient to connect it to the derivatives with small x. So this is what we write, and you can convert this again into vector notation. So you can write nabla of phi is equal to nabla naught of phi times f inverse. So this is the vector notation of this, which is also written, which can also be written taking the f to the front. It can also be written as, this is same as these two statements are the same. This can be taken to the front and then this becomes a transpose. So you can see that from here, you can write this expression. This is a scalar, this is a scalar. You can write this expression as fki inverse del phi del capital Xk, right? You can write it like this. Then this is transpose of f inverse times del phi del xk, which is this statement. So this statement and this statement are exactly the same. So this is how you convert the material gradient of a scalar to the spatial gradient of the scalar. Similarly, you can do the same things if you have a vector. So vector and tensor, let me show it for tensor. So our tensor, I have a second order tensor T, which is Ti j ei ej. We have done this before, and I want to find spatial gradient of T. So the spatial gradient of T would be del small xj of, so ej times del small xj of, let's say, T mn em em, right? So this would be written as del T mn by del xj, and then this ej and em will give you delta jm, and then you will be left with em. And T, the j will be knocked, the m will be knocked out in favor of j. So this is what you do, but here again, you can use T jn xj is equal to T Jn capital X, let's say K, del capital XK, del Xj. So you can write these gradients in terms of the material gradients now. And again, you can see that this is your F inverse. This is your F inverse. So this is the formula that you get as your connection between the spatial gradients and the material gradients. Please try these out yourself and let me know if you have a problem. Okay. Now, let's do a small problem. Again, my screen is not advancing. So the problem is I have a small sphere which has a radius epsilon, and it is subjected to a motion for which the deformation gradient, remember the deformation gradient is connects d small x to d capital X. So the deformation gradient is given by this tensor. Okay. Now I need to find the deformed shape of this body. What will I do? So, so this is how I will go about. So this, let us take this vector, the radius vector. Okay. And this radius vector is of length, let's say, dx1, dx2, dx3. So these are the components of this radius vector, so that the entire vector, which we can call epsilon, is dx1 e1 plus dx2 e2 plus dx3 e3. This is the vector, and I will plug it. This is the vector in the undeformed configuration. So I'll plug it in here, multiply it with f, and get the d small x. Now, in order to do that, I can do it in many ways. So I can convert this into a column matrix. So I can just write dx1, dx2, dx3 with this matrix, and I can multiply to get a 3 cross 1 vector, lambda 1 d capital X1, lambda 2 d capital X2, and lambda 3 d capital X3. This is what I get. Lambda 1, lambda 2, lambda 3, by the way, are constants. I can do it in the tensorial way as well. I can write f as lambda 1 e1 e1 plus lambda 2 e2 e2. Those of you who have done tensors would know this is how this particular quantity is written. And then I have this vector. So I will do f epsilon, which will be times so you can do this multiplication. When you do this multiplication, suppose this term with each of these terms, you have to remember that the last index here and the last base here and the base here will dot, and therefore whenever you have E2 or E3, this term will dot to 0. So you will get a result, non-zero result only from this term, which will be lambda 1 d capital X1 E1. So E1 dotted with E1 will give you 1, and then this E1 will be left. Similarly, E2 will give 0 here. E2 will give lambda 2 B capital X2.
Sir, you are not audible.
Hello?
Yes, sir.
Yes, sir.
Yes, you are audible, sir.
Yeah. How much did you see? I mean, I did not realize that I have been connected out. Hello?
Yes, last 1 minute only, sir.
So this, what I've written here is the same as what we have here. But as usual, please remember that whenever we represent a tensor as a matrix, we actually represent the particular components of the tensor in a particular coordinate system. Okay, so so while this is correct in this case, we have to remember that we have expressed things in this given coordinate system, and that's why we have got this tensor, this matrix representation of the tensor. Okay, so now whichever way you do it, this is your new deformed vector. So this radial line deforms into this line in the deformed configuration due to this deformation gradient. And then initially the sphere was given by dx1 square, dx2 square, dx3 square equal to epsilon square. And now, because you have components lambda 1 dx1, lambda 2 dx2, and lambda 3 dx3. So what you now have is dx1 by lambda 1 whole square plus dx2 by lambda 2 dx3 by lambda 3 equal to epsilon square. So here you put in d small x1, d small x2, and so on. So this is equation of an ellipse. So due to this deformation, this sphere becomes an ellipse, and that is not difficult to see, because if I write this, so you can try writing the motion corresponding to this. So remember, Fij is equal to d small xi d capital Xj. These are the components of Fij. You can try to write small xi as a function of capital Xj from this information given here, and you will see that what we are doing is what is known as a pure stretch. So we are pulling this in the x direction by a constant amount lambda 1, in the y direction by lambda 2, and in z direction by lambda 3. That's what we are doing. We're giving a constant stretch in all three directions. And that's why when you stretch a sphere by unequal quantities, it will become an ellipse. Okay. So, okay. Right. So let's do a more slightly more difficult problem. Again, my screen is stuck. I guess it. Okay. So here we have a slightly difficult, more difficult problem. So what is happening is I have this body, right? And I am, this is a rectangle, and I am deforming it into an arc of a circle. So I am bending it in the plane, in the arc of a circle. And I am doing it in such a way that, so these are the dimensions of, this is 2b and this is 2a, right? So I'm doing it in such a way that a line which is initially parallel to the x2 axis becomes a circumferential line. So this line is the map of this line in the deformed configuration. And similarly, lines that are parallel to the x1 axis become radial lines in the deformed configuration. So this is my mapping. Now, this is the domain of the reference body, and it has been deformed in this reference body is going to be deformed in such a way that this radius r is a function of capital X1 only. Remember that these vertical lines, which are at a distance of x1, capital X1, would be deformed into these circumferential lines. So R would be a function of x1 only. Theta would be a function of x2. So, so this is x2, and this would become the radial lines. So theta would be a function of x2, and z is, you can think of lambda to be equal to 1 for the time being. So z would remain as it is. So this plane won't move up or down. If lambda is not equal to 1, then it will move up or down, but there's no other deformation other than that. So we will ignore, we will not pay too much attention to the z axis for the time being, right? So now I need to find the deformation gradient for this case. Now here I will do, I will use the full power of tensors and try to write down the coordinates of a point, let's say this point, which is now located here. Coordinates of this point in the deformed configuration. The way I can do it is I can use these new coordinate systems, ER and E theta, the cylindrical polar coordinate systems, to write it. And EZ, of course, is coming out of the slide. So I can write the small x as R times ER plus Z times EZ, assuming that this is at a location Z out of the from the XY plane. Okay, so this is in polar coordinates. This is the location of a point in the deformed configuration. Okay, and now this is my initial configuration. And to remember, to calculate deformation gradient, I have to take this gradient. And this gradient in the Cartesian system is this vector. We have done it before in tensor, when we learned about tensors. So the gradient operator is this, with these as capital X's because of the 0 here. So I will have to now take, to calculate f, I will now have to take nabla 0 of small x, where small x is this quantity. So I will do it like any other multiplication. So I will write nabla 0 here. I'll treat it as a vector, and then small x is this. So when I do this, I will have to, so this term into the first term will give me E1 del capital X1 of RER. Now remember, these these basis vectors are not fixed basis vectors, not like E1, E2, E3. They are changing with position. So when I take derivative with respect to del x1, I have to ask myself whether ER is also a function of x1 or not. Okay. So if you look at it, ER is not a function of x1. So this would become del R del x1 times ER. When you do del x2 of RER, when you do del x2 of RER, you will do it like this, del R del x2 ER, and then there's a problem here. This should be R, right? So del R del x2 ER times R del ER del x2, and del ER del x2 is, as far as I remember, R e to the power e theta. Okay, so Z is easy. Z is a fixed vector. So Z, this would give you del Z del x1, del Z del x2, and del Z del x3, as it is done here. In case of only del x2 of ER, you have to be careful, and for our given motion, R is a function of x1 only, theta is a function of x2 only, and Z is a function of x3. So when we take these derivatives, del Z del x1, del R del x2, R is a function of x1. So these are 0, this is 0, this is also 0. So finally, you will end up with F in this space, E1, ER, E2, E theta, and E3, EZ space. You might think that's a strange space, but that's what we get. If you want to get it back in the E1, E2, E3 space completely, you will have to replace the expressions of ER, E theta, and EZ in terms of E1, E2, E3. In terms of E1, E2, E3, if you write ER, E theta, EZ, then you can further manipulate this expression and get an F completely in the E1, E2, E2, E3, E3, etc. space. Okay, so we are not doing that. This is good enough for us. So this is how in a formal way you can calculate your F. Okay, so you figure out what is your nabla 0, what kind of an operator your nabla 0 is. You figure out what your X is, and then if you do the multiplication systematically, you will be able to get your F. That's what exactly we have done. When you do that, make sure you know how to take derivatives of these base vectors, which are different from your E1, E2, E3 with respect to capital X1, capital X2, capital X3. Okay, so once you know how to do the derivatives, you can find the deformation gradient for any problem.
Sir, this in the last expression between E1 and ER and between E2 and E theta, what kind of like operator is it direct dot multiplication or?
This is dyadic. So this is E1 ER is what I mean by it is E1 dyadic ER. So you are writing a second order tensor in the E1 ER E2 E theta E3 EZ space.
Okay, sir.
Right. So that's what you are doing. Right. Okay. So let me stop recording for a moment. I'm sorry, this thing is getting stuck every time I try to share. Yeah, can you see the screen now?
Yes, sir.
Okay. Now, so this is about strains. So let me. So strains are basically associated with change in length. So we have talked about the motion, which is a mapping vector function of capital X and T. We have looked at the deformation gradient, which is the gradient of the motion. Okay. Now, what F does is it gives you d small x from map from d capital X. Okay. Now, strains are associated with changes in lengths and angles. So now we are asking that if the length of this small vector is d capital X dot d capital X, let's call this d capital S square. So this is the squared length of this small line segment. Then what is d small x times dotted with d small x? Let's call that d small s square. So what is the connection between d capital S square and d small s square? To see that, we will use this expression. We will use this expression, and we will see that there are many ways of answering this question. Now, one way of answering this question could be that let us define a strain, the difference between these two squared lengths. Okay, so let us define this we have called d small s square, and this we have called d capital S square, and the difference between them, let us call that the strain. So we are basically asking, at point capital X, there was a small line segment. It in the deformed configuration, it has some length. So my definition of strain is the final squared length minus the initial squared length. So what is that? What does that turn out to be? So to do that, we will do the following. So this d small x is d small x dot d small x. And this d capital X is d capital X dot d capital X. In initial notation, this would be dxk, dxk, and this would be d capital xk, d capital xk. Right? Now, this d small xk, I can write as f k p d capital xp, and this I can write as fk m, let's say, d capital X m. Remember, you have to change, these are repeated indices, so you should not use this more than 2 times. So this is how you can write it. And then okay, this is what I have done here. And then on this side, I have dxk minus d capital xk, d capital xk. And I have d xp and xm here. So this d capital xk, d capital xk, what I'll do is I'll write it as delta pk del xp. So I get this dxp, and then this one I want dxm. So I'll write delta mk dxm. So now I have dxp and dxm on both the terms. So I'll take dxp out. Then I have fkp, fkm, and then minus, I am left with delta pk times delta mk, but k knocks itself off, and I'll be left with delta pm and finally dxm. This is what I will left with from here. Okay.
So, sir, it's like F is operated on capital DX, right? So how come you have taken DX outside?
These are scalars. Each of these are scalars, right? I can change their order. I can move them around. These are scalars. This is component of a pth component of a small vector d capital X.
Okay, sir.
So these are scalars. So I move them around. So I am left with this quantity in the middle and dxp dxm. So convert this into a vector notation. So this can be converted into, so I have p here, p here. So I'll convert it into d capital X dotted with, what is this? This is fkp fkm. If it was f times f, then it would have been pk km. But since this is kp km, this is actually converts into f transpose f. And this, of course, is my I. And then it multiplies, this m multiplies with this m. So this is d capital X. So, this tensor is important for us. So I give it a name. I call it 2 times E, where E is defined as half of F transpose F minus I. And this is my first strain tensor. This is called a green Lagrange strain tensor. Now, what does it do? So this E operates on a small vector in the reference configuration and gives me the change in squared length of that small vector as it goes from the deformed to the current configuration. So it is a strain. This is a tensor that operates on a vector in the reference configuration. So this is a strain measure that operates on the reference configuration and gives me the strain, which I have defined as the difference in the squared length of the line. So this is a material strain tensor because it operates on d capital X and not on d small x. Okay. Is that okay?